All right, so this is assignment P for physics, 17.2. It's a PHET lab, exploring light as a wave. So let's view the assignment, not people's grades, the instructions. So we're going to go here, and it's going to open up this document, and we're supposed to go to this particular lab. So we'll go over here and we'll go to PHET. I did mean PHET. That's where I want to go. I want this to be a tab on my thing that I'm already working on. Thank you. And we're going to go to simulation. No. I want that to be right there. Can I not change that now? Oh, come on. Oh, well, whatever. I want to go to simulations. Want to go to simulations? Oh, here we go. All right. Let's get our mouse over here. Maybe sometimes it just doesn't like the touch screen stuff. So we'll have to just deal with that here. And what are we looking for? We are looking for waves interference. So we're going to go down here. Waves start with W. So we're going to go wave interference. We're going to open that one up. And we're going to start that. And then we're going to go, where'd our lab go? There's our lab, okay. So click on that. Okay, then we're going to look at diffraction first. Diffraction, all right. And then we're going to click on it again to start that up. And what is our lab asking us to do? Get familiar with all the controls, make changes, interact with the simulation. And then once you're familiar with the simulation, select the box and adjust the height so you get a tall, narrow opening. All right, so we're gonna, let's see, select the box and adjust it so we get a tall, narrow opening. Okay, so there we have so you got different shapes of things and different, these are all holes in a card. And what you're going to be doing is shining light through these various patterns of holes onto this other card to see what happens. So they want us to go here, and for each of these, you can change properties of them like that, right? But they want us to use that, and so I have adjusted that. So it is a long, tall slit. And now they want us to select a wavelength near one end of the color spectrum and turn the light. So here we go. We'll select a wavelength down here somewhere. I don't want it so dark I can't see it. Then I'm going to turn the light. Boom. All right. So as you can see, right up, see I can't draw because some interaction between the different software. This right here is the card, and it's shining a light on this right here, and so it's showing us that it's creating this here diffraction pattern. We're shining light through a slit, and it's creating a pattern. That's it. Now, why would it not just make a line? Why is it making this diffraction pattern instead? Well, that's what we're discovering, isn't it? So let's go back there to the mouse. Describe the diffraction pattern that happens. So take a moment to describe this. It's bright in the center, right? And then there's a dark line. It's like spaced between bright and dark and bright and dark, but it's brightest in the center. And you can see the diffraction pattern goes sideways, but it also goes up and down a little bit too. Very interesting. How is the diffraction pattern oriented relative to the opening? So the opening is up and down, but the diffraction pattern looks, you can see the up and down one a little bit, but it looks primarily side to side. And then it says to make the opening short and wide and see what happens. So we'll do that. Okay, so we have the same pattern, only it's oriented up and down, which is still perpendicular to the slit that we're observing. So that's really interesting, isn't it? And you see, describe that. By the way, if I remember right, this is a long lab. So the diffraction pattern oriented appears to be like perpendicular, doesn't it? Now max out the width and the height and describe the pattern that appears. So now we're going to go like this. Now what's appearing? Well, it's a cross-shaped diffraction pattern. That's interesting too, isn't it? I wonder what would be going on in the light that would make that happen. So how is that diffraction pattern oriented and what's it look like? Describe, now minimize the height and width of the opening. So see, they're teaching you to play and to experiment. All right. Oh, look, isn't that interesting? Look, when it's big, the diffraction, whoops, I want to do that. When it's big, the diffraction pattern is small. And when it's small, the diffraction pattern gets big. Come on, that's interesting. You know it is. All right. Now change the wavelength to the other side of the spectrum and see what happens. So let's, I guess, yeah, we'll just leave it like that right now and we'll just slide it over. And I think maybe in sliding it, sometimes when you slide something, you can see if any important changes are happening even as you move it. So let's just watch. It's growing, isn't it? Look at that. That's very interesting. So, and if you remember, maybe you don't remember, but the blue is the shortest wavelength, and the red over here, that's going to be the longest wavelength. The lowest frequency, longest wavelength. This is a higher frequency, shorter wavelength. In fact, you can see the wavelength up there. That says that's 400-ish nanometers, and that's like almost 800 nanometers, 750. So longer wavelength, lower frequency, has a larger diffraction pattern, and that's pretty interesting, I think. I guess we were already supposed to have done something like this. Look at that. Okay, let's just change it again. So that's okay. That gets super apparent, doesn't it? You can really see how much bigger that thing gets with the lower frequency waves. The red waves are much lower frequency. And then it wants you to go through that pattern and just kind of describe those patterns and explain how this shows that light behaves like a wave. And if you remember, that waves interfere with each other, right? And then waves also, waves bend. And I can't, I'm sorry that I cannot draw, but I can't. So if you picture a wave going through the slot, one of the things we have is waves bend around openings a little bit. And so that's what's going on here. The light is actually refracting or diffracting around the opening of that slit. And so what you're seeing there is the pattern that the slit creates, because when the light diffracts around the opening, it creates like two semicircular waves that are just like waves in a pool. And the waves, in some places, they add up together. That's the superposition of waves, we call that. The interference of the waves. Sometimes they add together, sometimes they cancel each other out. And that's what's happening here with the waves. And as I do that, there's oops, didn't mean that happen. As I do that, I'm creating different ways in which that refraction around the edge is creating different waves. And you're going to see that more in a moment. But that's what's happening. Interference. See, they kind of ask you, about interference before they walk you through interference. So let's do the interference one now. And we got to go here. Okay. So, and I think it's all going to be, we need to select light. So right now it's on water, I think. Yeah, look at that, water. Okay, stop. Well, let's do water real quick because water is clearly a wave, right? And so you can see there are crests and troughs, and where the crests meet in the middle, it's really bright, and then towards the corners, like right in here, I hope you can see that right in there. That's where the crest and the trough is lining up. And I wonder if you can drag them. You can't move those. Okay. So that is, where do I change it to light? Okay, there we go. Okay, so here's what happens with sound. And you can see the same thing happening with the sound waves. The bright parts are the high intensity where the waves are adding together, and then the dark parts are the troughs. And you can see in this middle area right here, they're kind of canceling each other out, right? That's the interference, and that happens with waves of all types. What am I? I'm looking. Oh, what? There it is. Light. Okay, so now we got light. And we're looking at light, and we're going to set the amplitude in the middle. Amplitude corresponds to how intense something is. So we're going to, right now it's at the max. It says to set the amplitude in the middle. Select the light amplitude in the middle. Turn on the screen. The screen is going to be this detector in the back right there that's going to show how the light is either the waves are adding together or subtracting. Pick a color with the frequency slider and write the color you choose. Now turn on one of the lights, okay? So I'm just gonna I'll use green. Turn on one of the lights, boom. Okay, so there's a light. It's like a light bulb. The wave is just going out there, right? And now we're looking at the screen. I feel like the screen should be showing us something. If we turn that on really bright. No, it's just lighting up the whole thing, right? Because the wave is striking the whole screen. Oh, there we go. I finally got some on there, but it's pretty much kind of lighting the whole thing evenly, right? You can see little banding in there, and I'm not sure where that banding is coming from. I'm not even sure if that's not just an artifact of the software, because that's one light, and you should see the whole thing lighting that screen evenly. And it says to describe how you can determine the wavelength of the color of light you choose. Okay, so the wavelength, let's see, that's the separation between the two. How do you determine the wavelength of this? Well, we know how fast. Well, can we just do that? What's it asking for again? The wavelength. So we have I honestly don't see how you can get that directly. We've got the separation. With light travels as fast as light travels. There must be a way, right? But it's Thursday at the end of the quarter, and you and I do not have time to figure this out together. So let's click graph and see what happens. Okay, so we can hit pause. Okay, so now we can see the wavelength. It's just, see the position is in nanometers. And if I'm looking at this peak right here, That's just basically right on the 3000 nanometer mark, right? And this peak is right before the 2500. So 3000 minus a little more than 2500. I'm going to call that about 550 nanometers. So that's going to be the wavelength of the light, 550 nanometers. And then you can, the wavelength is 1 over the frequency. So you can figure that out. What's it doing here? Oh, we didn't click intensity. Okay, turn that up. So now we're getting an intensity graph. Okay, so yeah, we turn up the amplitude and the intensity of we see the intensity going up, right? Which is what you would expect. And there's a little fluctuations there, and I'm not sure why those are there, to tell you the truth. But, so we maxed out and the intensity chart changes, pick a new color with the frequency slider, not amplitude, let's pick a new color, there. And now we can get the wavelength and frequency there. We can just pause it. Step it forward until you get one lined up where, oops. Okay, so that one's lined up at about 3000. And this one's going to be what? That's going to be more like, the other one was 550. This one looks more like maybe from here to here is about 700, right? 700 nanometers would be the wavelength here. So you figure out the frequency from that. What else do they want us to do? This is actually a pretty complicated lab to go through super quickly. So just take a good try at it and kind of learn how the light behaves. I'm not so concerned about the math. So I'm going to take the graph off there now, and I'm going to leave that up there, and I'm going to start this up, and I'm going to start the other light up. And what I'm going to start this other light up in a moment. Now, what I want you to, let's see, turn on the other light. Okay, that's where we are, 13, and describe what happens. What's going to happen when I turn on the other light? Knowing what you know about wave interference, what's going to happen? Just like the water, just like the sound, the electromagnetic waves are interfering with each other too, right? What do we see on the graph? The intensity graph is showing us the places of high intensity and low intensity light because they are also interacting with each other in constructive and destructive interference, right? And we can turn that way up and we'll see that that's what happens. The highs get higher and the lows are still zero. Then it says to separate them more and see what happens. So we'll separate them more. Are we going to see more bumps or less? Quick, before they get there, more bumps or less? More, right? Because these are at more of an, by the time you're looking at this, and by the time these interact, they're hitting at more of an angle like this, so there's going to be more bumps there, right? There's more space to interact with. And if I put them way together, what's going to look like? Well, they're almost parallel, right? So there's almost going to be nothing there. It's more intense right in the middle. And then I can move it back out there, right? So, vary the amplitude, that's going to change the intensity. Vary the frequency, what effect does that have? So let's just, let's put them sort of midway distance apart, and we'll watch this and see where what happens. Now, that's a low frequency wave, right? That's a, red. Now, what if I change it up to a high frequency wave? Am I going to get more or less or the same number of bumps in my diffraction pattern here? Not the diffraction pattern, the wave interference pattern. Oh, I guess I can't. You're gonna have to like look at it. Okay, remember there's like 3 bumps, right? Now, how about if I do that? More bumps or less? Quick, before you see it, more bumps or less? A lot more. Look at that. Because the higher frequency wave has less space between each wave, so they're hitting more frequently, which allows them to interact more frequently like that, right? So let's see what else. We could adjust the brightness, and then they want us, this is a lab and a half. So again, at Thursday, coming up here at the end, just do your best, do some stuff and see what happens. So now we're going to go to slits. And what you're going to find out is that those slits, these are point sources of light here, like a light bulb. And what you're going to find out is that the light goes straight, the light wave might be coming straight through those slits, but when it goes through the slits, it's going to diffract around. When it goes around the edge, it's going to end up, and like a point, it's going to end up making a rounded thing. Yeah, I'm a science teacher. But see, you can see what's happening there. You can. Oh, we don't want water. We want. What do we change? Light. It does the same thing. Why? Because it's a wave. Only now we're talking electromagnetic waves, and we can think about the. Let's put the screen up there with the intensity graph again. Okay, so you can see that as the light goes through the slit, the same exact thing happens. It's doing its little refraction bit, and when it hits those points, it bends outward. And then play with it. We'll see what happens. See, it only does it around right at the edge where it bends around, right? So you can see the straight part right here. There's nothing really happening to this part. It's just right. Whoops, I didn't mean to do that. It's just right here at the edge. It starts to bend around that way like that, right? We don't need to have that big amplitude there. So we can, and then we change this, and the closer you get to the narrower the slit, the more it's going to act like a point source with the light, the wave, and this happens with water waves or anything. It's gonna refract around. It's gonna bend around the edges of this thing right here. It's gonna bend around those edges, and it's gonna turn it circular. So now let's go to 2 slits, and you know what's going to happen with 2 slits already without thinking about it, because we've already seen it happen with the lights, right? So now what's going to happen with the slits? It's going to be the same thing. And there we go. We can see that same kind of pattern going on, right? And the slits, and because they end up acting just like point sources of light. If the slits are narrow, what happens if they're wide? Well, then we don't get as much of an interference pattern toward the center of this thing, right? Because that's just acting like a straight line right there. Although some of this is kind of bleeding over into there, right? You can see that, and some of this is kind of bleeding over into there, because remember, this is going off like that. So what happens if we make the slits narrow again, and then we separate them? How many peaks? Lots, right? Just like in the other one. What if we make the slits wide? There's almost no wave interference along here, almost no wave interference along here, but it is bending around there, right? So we have a little bit of wave. We're getting a little bit of that light right here, adding up to a small bump right there, right? A little bit of intensity there, but most of it's just coming straight through that wide open barrier. So, again, I'm just, at this point, I'm telling you, don't worry about the math. What do they want us to look at? One slit of 200 nanometers. And they want us to slide that screen. One slit, 200 nanometers. And they want us to slide the screen toward here and see what happens. Okay, now we're going to slide it away and see what happens. Okay, we're looking at the intensity. It's just a little bump there. What happens if we do there? It's going to be less, right? Because see, this energy is spreading out. There's a certain amount of energy coming out of that hole, right? And if you get it close to the barrier, you're getting a large concentration of the energy. But now the energy's spreading out over further and further and further. It's spreading out wider and wider. So here, if we do that, we're definitely going to get most of the energy striking this thing, right? But if we do this amount of energy that's right there as it moves out, spreads out, spreads out, spreads out, spreads out. So it's just not very strong by the time it hits that. Okay, so just follow the instructions there. It's just got real clear numerical instructions about moving the slit back and forward. And do think about it. And if you want to do the math, you can. But I am out of time to explain that. And I really want you to just see the behavior of the waves and get a feel for it more than do the math at this point. So that's all I'm going to do with that. And on to the next one. Bye-bye.